Hello everyone, welcome to my video series on Wilcoxon rank sum test. So in this video we are going to talk about Fisher's exact test. So without further ado, let's dive in. Let's start with a simple example of 20 balls. So what does ball have to do with Fisher's exact test? So Fisher's exact test is based on probability calculation and some formula. So in this example, we are going to see how that formula is actually derived. So suppose there are 20 balls and 9 of them are red and 11 of them are green. So suppose that you randomly picked up 10 balls from these 20 balls. So you have 20 balls right here and you have picked up 10 balls randomly. So the question is, what is the probability of you getting 8 red balls and 2 green balls? Okay, so among these 10 balls, you have to have 8 red balls and 2 green balls. And what is the probability of getting that? And you can see that this entire scenario can be represented using this nice 2 by 2 table. So you have red balls and you have green balls, and some of them are picked and some of them are unpicked. For example, you have been able to pick 8 red balls, so 8 is here, and 1 red ball hasn't been picked. 2 of the green balls have been picked, and the rest of the 9 haven't been picked. So these are the total number of red balls and total number of green balls, which we can see right here as well. Now, why have I presented it in this way is actually very important, because in the Fisher's exact test, we are going to see tables which look exactly like this. Now, let's actually see how do we actually get the probability of getting 8 red balls and 2 green balls. The first thing is, what is the total number of ways we can choose 10 balls from the collection of 20 balls. It doesn't matter whether, how many of those 10 balls are green, how many of those 10 balls are red. It doesn't matter. We just want to know how many ways in total we can actually choose those 10 balls irrespective of their color. So it's the total sample space. So it is nothing but 20C10. So if you know combinatorial, then you know that this is going to be 20C10. But we need to get 8 red balls and 2 green balls. This is our requirement. So there are 9C8 number of ways we can choose 8 red balls from the existing 9 red balls. I'm sorry about this. Here it should be red. I have mistakenly given green here. But anyway, let's continue. And similarly, we can choose 2 green balls. We can choose our 2 green balls in 11C2 ways from the collection of 11 green balls, right? I think this is very easy to understand. Anyone who knows permutation combination understands this. So the number of ways we can make these two choices is basically multiplication, right? It is multiplication. So the way to get the probability is to divide this number of ways by the total number of ways. So this is going to be the probability, and this is going to be 0.00268. Okay, I think this is quite intuitive. Now, if you don't understand what I'm talking about here quite yet, then I would suggest you to look at my video on hypergeometric distribution. It is part of my probability distribution series, and I'm going to leave the link of that video in the description. Okay, now let's look at the actual example where we are going to apply the Fisher's exact test. So let's look at this table. It's also a 2 into 2 table. There are smokers and non-smokers. So these two values are basically of smoking status attribute or smoking status categorical variable, and cancer or no cancer is actually the part of cancer status. So these are two values of cancer status categorical variable. And we can see these numbers. So that means 8 of the smokers has cancer, 2 of the smokers do not have cancer, right? Now, do you feel the similarity of these numbers to what we saw in the previous slide? I think you do, right? Because in the previous slide, we also showed something very similar, where cancer can be replaced by the red balls and no cancer can be replaced by the green balls, right? So basically, we are going to calculate these probabilities exactly like the way we did before. If you have this kind of 2 by 2 table, that means your categorical variables each have 2 values. For example, here, smoking status has smoker and non-smoker, while cancer status has cancer and no cancer. And some of these cells will have less than 5 samples. If you have that kind of scenario of small sample number and 2 by 2 case, then you can actually use Fisher's exact test. And there are many cases where you are going to face this kind of scenario, especially if you are dealing with bioinformatics. So the question we are trying to understand or trying to answer here is, are two categorical variables significantly correlated, right? For this case, The question is sort of like this. So we provide the null hypothesis, which is smoking and cancer are not dependent. That means they're independent. They have no correlation with each other. The alternate hypothesis can be that smoking increases cancer risk, right? That can be the hypothesis. So you can see that we have strictly mentioned increases here. That means it is a one-sided test, right? And part one of this video series, I have mentioned what one-sided test and two-sided test is. But if we just wrote that smoking and cancer risk are correlated, then that would be two-sided test, right? But in this example, let's just look at one-sided test case. Okay. Now we know how to get the probability from this table because we have worked out the math in the previous slide where we gave the example of balls, red and green balls. So we are simply going to choose these 8 cancer balls basically, or 8 cancer patients from the 9 that is remaining, and 2 non-cancer patients from the 11 non-cancer patient that we have. And then we are gonna take the total number of ways we can choose them from, and so that will give us this probability. Now if I would just show this table to you before and start from there, I don't think the whole thing would be that intuitive. So I decided to go to the ball route first and then come here. I hope that it helps. Okay, now what is the p-value? Is this the p-value? Actually, the answer is no, it is not the p-value. P-value is the probability of this table or more extreme cases happening. So it's an extreme case, right? I think we can all agree that it's to some extent an extreme case because almost all smokers are getting cancer and almost no smokers, I mean non-smokers, are not getting cancer at all. So almost all non-smokers are having no cancer. So it's an extreme case, right? So we want to get the probability of this case plus all other cases which are even more extreme. That is basically the p-value of one-sided test at least. Okay, so the important question that we try to understand here is what does it mean by more extreme case, right? So a more extreme case is basically a case or cases, there can be multiple more extreme cases where we have even more smokers getting cancer while maintaining the current row and column level sums. So this is very important to understand. This difference right here should be even more extreme, but these sums, so column level sums like 9 and 11 and row level sums like 10 and 10, these has to be the same. This is very important. You cannot say that, okay, let's change this sum. You cannot do that. You have to alter these numbers such that these sums, these 4 sums are actually the same. So let's see what is a more extreme case in this respect. So what we have done here is we have said that, okay, right now 9 of the 10 smokers will get cancer, but none of the non-smokers will get cancer. So it's even a more extreme case, more extreme disparity. So in such a case, we can get the probability just like before, 9C9 into 11C1 divided by 20C10, just like before. And so we are going to get this probability. So now the question is, can we get an even more extreme case? It's not possible because if we give 10 here, if we write 10 here, then this has to be -1. And minus cannot, I mean, there cannot be negative number of cancer people, right? That's not possible. So this is as extreme as it gets right here. But again, just to clarify, there can be examples where we have 2, 3, 5, 10, or even 10 more extreme cases. In that case, we are going to have to make those tables and calculate probability as well. So the p-value will be the summation of these two extreme case probabilities, which is 0.00274. It is obviously less than the significance level of 0.05. So we can reject the null hypothesis and we can say that smoking indeed significantly increases cancer risk, right? So we have been able to the positive association between smoking status and cancer status, categorical variable. So here are a few things. If you have more than 2 cases, more than 2 values, I would say, per categorical variable, right? So what do I mean by that? For example, here smoking status had 2 values, smoker and non-smoker. But if they had like 3 or more values, then it wouldn't be very smart to do this kind of Fisher's exact test. And also, if you have more than 5 samples in all of your 2 by 2 cells, then it will also not be very smart to do this Fisher's exact test. It is because in those cases there will be too many more extreme cases to consider, and also often these calculations become very tedious, and then you are going to have values right here, or you are going to have such big values right here that you are going to get math error or something like that. So I wouldn't recommend you to use Fisher's exact test if you have these 2 cases. So what are you going to use in these cases? I've already mentioned this in part 6 of the video series. We have talked about chi-square test. So you can actually use chi-square test to do the same thing. But again, chi-square test is based on expectation and it's an approximation. It's a quick approximation, a fast approximation. So it will only apply that if you have like more than two values per categorical variable and more than five samples for every cell of your 2 by 2 cell or 3 by 3 cell or whatever cell you have. So that's it for this video. Hope to see you in the next video. If you like the video, feel free to subscribe and share, and you can donate to our channel to support our content. Thank you very much.